Good afternoon, everyone. Welcome to this afternoon session. We are very happy to have Professor Takuro Mochizuki from Kyoto University, and he will be talking about some applications of non-abelian Hodge theory. So, please join me in welcoming him.
Thank you for the introduction. And so it's my great pleasure to give a talk in ICBS of this year. I thank the organizers for inviting me and for giving me this opportunity. Today we shall discuss about some applications of non-abelian Hodge theory to the study of holomic D-modules over higher dimensional complex varieties. So first of all, let me remind you the beginning of the non-abelian Hodge theories. So we consider a Higgs bundle E theta or a complex manifold. So it means E denotes a holomorphic vector bundle and theta denotes a holomorphic end-value holomorphic one form such that theta which theta is zero. And let H denote a Hermitian metric of okay, okay. So, so we consider Hermitian metric of the vector bundle. Then we obtain the charm connection, that is a unitary connection determined by the Hermitian metric and the holomorphic structure of the vector bundle. And we also have the adjoint of the Higgs field. So we obtain another connection denoted by D1H as the sum of the charm connection and Higgs field and its adjoint. And the Hermitian metric is called a pre-harmonic metric of the Higgs bundle if this connection is flat. And Higgs bundle with a pre-harmonic metric is called a harmonic bundle. So by definition, harmonic bundle has the underlying Higgs bundle, and it also has the underlying flat bundle. And if the base space is a complex projective manifold, by this correspondence, we obtain equivalencies of harmonic bundles and Higgs bundles and flat bundles. More precisely, we obtain equivalencies of irreducible harmonic bundles and Higgs bundles satisfying a stability condition and the vanishing of the higher Chern characters and simple flat bundles. And this is a fundamental theorem of Corret and Simpson. And if the base space is one-dimensional and the rank of the bundle is 2, it is due to Donaldson and Hitch. And this is the beginning of the non-abelian Hodge theory. And let me mention, by this correspondence, we also obtain the homeomorphism of the moduli spaces. And the moduli space of flat bundles can be considered as the first cohomology with GLN coefficient. And the homeomorphisms can be considered as an analog of the Hodge decomposition of the standard cohomology group with C coefficient. So this is one of the reasons why this theory is called non-abelian Hodge theory. And the non-abelian Hodge theory has been a very big research area. And there are many interesting studies, especially for the modular spaces of flat bundles and Higgs bundles on compact Riemann surfaces. I mean, in the case, the base space is one-dimensional. But there is also one branch of the non-abelian Hodge theories about harmonic bundles with singularity over higher dimensional complex manifolds, which is guided by Simpson's meta theorem. So in this talk, we shall discuss ongoing investigations about some applications of this branch of the non-abelian Hodge theory. So in the following of my talk, first I will give a very brief review of this branch of the non-abelian Hodge theory. And after the review, my talk will consist of two parts. In the first part, we shall discuss a generalization of Bannikov-Kontsevich theorem to the non-algebraic setting. And in the second part, we shall discuss irregular Hodge theory and its application to the rigidity of meromorphic flat bundles. So let me give you a brief review. So first, let me remind you twistor structures and Simpson meta theorem. Twistor structure is a holomorphic vector bundle on twistor structure is a holomorphic vector bundle on P1. And from a twistor structure, we obtain a vector space as the fiber over 1, and we regard twistor structure as a structure of the vector space. And the twistor structure can be considered as a generalization of twistor structure can be considered as a generalization of Hodge structures in the following sense. So complex Hodge structure consists of a complex vector space equipped with two decreasing filtrations. And by applying the least construction, we obtain free C lambda module from one filtration, and we also have obtained a free C lambda inverse module from another filtration. And we can regard free C lambda module as a vector bundle on C. And we can regard free C lambda inverse module as a vector bundle on P1 minus 0. And they are the same on C star, P1 minus 0 infinity. So by patching two vector bundles, we obtain a twistor structure. So in this way, complex Hodge structure induces a twistor structure. And by this construction, Hodge structures are equivalent to C star equivalent to twistor structure. So in this sense, twistor structure is a generalization or underlying structure of complex Hodge structures. And Simpson proposed a very important principle called Simpson's meta theorem, which says any concepts and theorems for Hodge structure could be generalized to the context of twistor structure. So for example, we can consider pure twistor structure or mixed twistor structures as a twistor version of pure Hodge structures and mixed Hodge structures. And Simpson reformulated harmonic bundles as polarized variation of pure twistor structure. That is a twistor version of polarized variation of Hodge structure, pure Hodge structures. And more roughly, it allowed us to consider harmonic bundles as flat bundles equipped with pure twistor structure. So we are guided to consider analog of harmonic bundles in the context of holomic D modules, which are flat bundles with singularities. So we recall the notion of holomic D modules. So let dx denotes the shape of holomorphic linear differential operator of x. So and it is naturally a shape of algebra. So we can call a shape of left modules over dx is called the dx modules or d modules on x. Then from a coherent d module on M, and from a coherent d module on x, so by taking root filtration, we obtain a coherent O module on the cotangent one of the x. It is a kind of the classical limit of d module. And it depends on the choice of good filtrations. But the support of the limit or support of this coherent O module is independent of the choice of good filtration. It is well defined for the D module M. And it is called the characteristic variety of the D module. And according to the fundamental theorem of Sato and Kashiwara and Kawai, which was later proved by Gaba much more easily, but anyway, according to their fundamental theorem, the characteristic variety is coisotropic with respect to the natural symplectic structure of the cotangent bundle. So, and if the characteristic variety is Lagrangian, the D module is called holonomic. So holonomic D module is defined to be some minimality property. And so the holonomic D module has many interesting properties. For example, it shares many important properties of ordinary differential equations. And one of the important features of holonomic D modules is a nice functorial properties. Namely, for instance, in the algebraic case, there exists the Grothendieck style standard functors. For example, if we are given a morphism of algebraic varieties, or smooth algebraic varieties, we have the direct image functors and the inverse image functors. It is a derived category of conic D modules. And there are also tensor product and inner product for some useful functors. Sorry, could you repeat? Yeah, so this obviously depends on the choice of filtrations, but the support of this module is independent of the choice of filtrations. So the characteristic variety is independent of the choice of filtrations. And the theory of mixed twistor D modules has been developed by Saba and myself as the twistor version, mixed Hodge modules due to Moriko Saito, inspired by Simpson's meta theorem. And very roughly speaking, mixed twistor D module is economic D module equipped with mixed twistor structures. And unfortunately, it's not easy to explain the precise definition of mixed twistor D module. So instead, let me explain just one important ingredient for mixed twistor D module. So let Rx denote the sheaf of associative algebras of C delta times X obtained as a canonical deformation of the symmetric product of the tangent sheaf of X. More explicitly, let Rx denote the sheaf of subalgebras of D C lambda times X generated by lambda times the pullback of the tangent sheaf. For example, if X is an open subset of Cn, Rx is generated by lambda times del P over the structure sheaf. And the lambda del P and the coordinate function GQ satisfy this commutation relations. So in this sense, Rx is the canonical deformation of the symmetric tensor product of the tangent sheaf. And the mixed twistor D module of X is formulated as an Rx module with some additional data satisfying some conditions. I'm sorry, this does not say anything, but let me say an important condition is the R module underlying mixed twistor D module is flat over OC lambda. So it will appear later. So in particular, if X is a point, then R module underlying mixed twistor D module is a locally free OC lambda module of finite rank. And there are two important results in the theory of mixed twistor D modules. One is a nice functoriality. As I mentioned, there are useful functors for algebraic economic D modules. And such useful standard functors are enhanced to the functors for algebraic mixed twistor D modules. So this is one important result. And another important result is a generalization of the theorem of Corret and Donato and Kitcher and Simpson to the context of twistor D modules. I mean, on a projective manifold X, we have equivalences between semi-simple economic D modules and polarized pure twistor D modules. Let me remark. So for this functoriality is stated for mixed twistor D modules. But we can prove that the direct image by projective morphisms preserve all the pure twistor D modules. And so by this characterization, we can show semi-simplicity is preserved by the pushback by projective morphisms. So this was all the main application of the theory of twistor D modules. But in this talk, we shall discuss some other applications which we are studying more recent. Sorry, proper here. we don't, projectivity is not so important, but we need some algebraic sphere functions. Yeah, so it's a convenience to consider on projective manifold. Yes. Maybe. Yeah, thanks for asking. So we'd like to discuss two applications. One is a generalization of Barnikov continuity theorem. So we consider a complex manifold with holomorphic function f. And we assume the set of the critical point is compact. And there are several interesting objects associated with such pair of x and f. And one of the most basic is a twisted Brownian complex and its cohomology group. So let omega xk denotes the sheaf of holomorphic k forms on x. Then we have the exterior derivative, and we also have the morphism induced by the exterior product of the df. And let omega xk lambda denotes the sheaf of formal power series with omega xk coefficients. Then with the differential lambda d plus df, we obtain the sheaf of a complex of sheaves of x. And it is called the twisted Brownian complex, or formal twisted Brownian complex, when you'd like to emphasize to consider formal power series. And its cohomology group is called twisted Brownian cohomology, and which is naturally a module over the ring of formal power series. And there are several different versions of twisted Brownian complexes. For example, if x and f are algebraic, then it is also natural to consider the sheaf of polynomials whose coefficients are algebraic differential k forms. So in this way, we also obtain the algebraic version of twisted Brownian complex and its cohomology groups. Then for twisted, please. Sorry, so sorry. Yeah. Yeah. In algebraic setting, a polynomial it is natural to consider, and of course we can consider polynomial setting even in the general case, but it's better to consider formal case here. I mean, it's not so useful to consider polynomial version here. And in the algebraic case, so the polynomial means, so in some sense, this we'd like to consider, so for polynomial version, in some sense, we'd like to consider some objects on x times c lambda. And so in the algebraic version, so it's natural to consider polynomials. But and of course, even in the general case, we can consider we can consider polynomial versions. But so let me show you the next slide. So one of the basic questions about concerning twisted drum complex cohomology is sorry, is the E1 designation of the associated spectral sequence. And if we consider a formal version, then it is the E1 designation is equivalent to the freeness of the twisted drum complex cohomology groups. But if we consider polynomial version, it's not equivalent to the E1 designation in general. So that is one of the reasons it's better to consider the formal version in this setting. Yeah. So let me continue my talk. So as I mentioned now, so one of the basic questions on the twisted drum cohomology group is to ask whether the twisted drum cohomology group is free of finite rank over the ring of formal power series. And so actually, it is a basic question in the non-commutative Hodge theory of constraints and its collaborators. And it is replaced in terms of the even degeneration of some spectral sequence. I mean, we obtain the decreasing filtration by considering the subcomplex generated by lambda j. And so we obtain the associated spectral sequence, which is often called Hodgson-Drum spectral sequence. And the even term is given in this way. Then this question is equivalent to ask the even degeneration of this spectral sequence. Yeah, and as I mentioned, so this if we consider polynomial version, it is not equivalent to J. J can't go to 0 to J. J, yeah, yeah. It's not finite. Yeah, yeah, not finite, yeah. But how to say? So we have some range of the spectral sequence, yeah, and so for some direction it is infinite, but for some direction it's finite, and so the spectral sequence degenerates at least in several finite stages. But anyway, so this question and this question are equivalent. No, 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 no. Yeah, so sorry, I don't know how to answer, but this it could it's so this is free if and only if this spectral sequence degenerates. So or at least if free and this is actionic, if and only if this is spectral, this degenerates at one stage. So yeah, so maybe we can discuss. So this is so for related to this question, there are two classical results. One appeared in the Hodge theories. So if x is projective and f equals 0, then the even determination, the desired even determination followed from the Hodge decomposition of the homology group of projective varieties, which followed from which was obtained by which was observed by Doreen. And in this case, more strongly, we obtain the freeness of the algebraic version of treated cohomology groups. And, and later, Doreen and Inuti developed a method to obtain these results by using the reduction to positive characteristic instead of the instead of Hodge theories. And another classical result appears singularity theory. If the critical point set consists of just one point, then the even degeneration falls, because in this case, this cohomology group vanishes unless L equals the dimension of x. So in this case, the even degeneration holds almost by almost trivial reason. And let me remind you, this even degeneration is, and its generalizations are very fundamental in the theory of, in the Hodge theories. And it is also useful to, for example, to obtain some vanishing theorems. And this even degeneration in singularity theory is also very important. For example, as a starting point of the deep theory of George Saito about primitive forms. So this question is related with very deep aspects of mathematics. And the modern study about the twisted drum homology was opened by the theorem of Barnikov and Konstantin. So suppose X and F are algebraic and F induces a projective morphism from X to C. Then they established the even determination holds. And more strongly, in this case, we obtain the algebraic version of twisted homology group is free. And this type of theorem is very important and fundamental in the non-commutative Hodge theory of Cornelius and his collaborators. For example, it is essential in the proof of smoothness of some moduli spaces associated to random variable models. And as far as I know, the proof of Barney-Kaufman constraint has not yet been published, but it is known it is obtained by generalization of the method of linear illusion. And the theorem of Barney-Kaufman constraint has attracted many mathematicians because it is interesting and it is all because it is and it is also related with many various fields of mathematics. Actually, another alternative proofs were given by Saba by using Hodge modules and micro-localization, and by August and Borobotsky by using their Simpson corresponders or non-abelian Hodge corresponders in positive characteristics. And more recently, Arintin and Caldararo and Havlicek revisited the theorem of Barney-Kaufman constraints in their study of the linear illusion method from the viewpoint of derived algebraic geometry. And there are also intensive studies about the L2 version of the twisted lamp complex studied by Lesniewski and more recently by Fan and Leven. And they established even degeneration or more stronger properties in this L2 version of twisted lamp complexes. And let me remark, in these studies, some conditions are imposed on the behavior of X and F around infinity. So we shall return to this point later. And let me mention, the theory of twisted modules is also one of the natural framework to study Barney-Kaufman constraint theorem, at least in the algebraic case. So let X denote algebraic morphism from projective morphism from X to C. In the case of Barney-Kaufman constraint theorem. And so it extends to a projective morphism from X bar to P bar, such that the inverse image of infinity is normal crossing. Then we have we obtain the Rx bar module given by the family of integrable connection given by dx plus lambda inverse dx. So I don't explain the detail, but by considering this kind of family of meromorphic family of integrable connections, we can construct R modules. And in this case, this underlies mixed study module X bar. We consider the morphism from X bar to point. I mean, the morphism by correcting X bar to a point. And then the direct image of LF by AX bar is isomorphic to the direct image of the analytic version of the twisted lamp complex by identity times AX bar. Then, so by the factorial to mixed twisted modules, this guy also underlies a mixed twisted module on point. It means this is a locally free Cauchy lambda modules. And it implies a Barney-Kaufman constraint theory. So by using the twist theory of mixed twisted modules, we can revisit Barney-Kaufman constraint theorem in the algebraic case. And we can also obtain a generalization of the Barney-Kaufman constraint theorem to the non-algebraic case. I mean, the even degeneration holds when X is scalar. I mean, this condition is just considering a neighborhood of the set of critical points. So in the previous studies, some conditions are imposed around infinity of x and a. But in this case, we consider we need the condition only around critical point, the set of the critical points. And we have to study the following two issues for this story. The first one is, so as I mentioned, we need we need uh, we need a new argument so that we can ignore the behavior of x and f around infinity. And the second point is, so as I in the review, I mentioned the mixed tree module has some nice factorial property, but it is just given in the algebraic setting. So we need to prove mixed tree modules are preserved by the direct image by some no algebraic morphisms under appropriate conditions. So we'd like to define the theory of mixed tree modules. And for the second point, we obtain the following theorem. So we consider a morphism of complex manifold and assume X is scalar. And we consider a regular mixed tree module on X. Regular means the underlying D module is the underlying conic D module is regular. And we suppose the support of the mixed tree module is proper over the target space Y. Then the cohomological direct image also of this regular mixed tree modules are also regular mixed tree modules of Y. So for this theorem, we don't need the algebraicity. And for this theorem, it is essential, or the important point is a generalization of Kashiwara-Kawai theorem. So let me explain. So let's leave a complex manifold with a simple normal crossing hypersurface. And so let E be denote an RZ module underlying a polarized regular persistent module on Z, such that the stoic support of E is C lambda times Z, and its restriction to C lambda times Z minus H is a holomorphic vector bundle. And let me mark this vector bundle is equipped with a Hermitian metric induced by polarization. And then we have two natural complexes of shifts on C lambda times Z. One is given by the drum complex of RZ module. And the other is the drum complex of this vector bundle induced by this vector bundle and the metric H and the RZ module structure. And the first one is adapted to the theory of mixed tree module. And the second one is adapted to the harmonic theory. And, and the theorem is that these two complexes are naturally quasi-isomorphic on C lambda times Z. Let me remark, there is a very famous theorem of Kaplan-Schmidt and Kashiwara-Kawai, which says there exists a quasi-isomorphism of this kind of isomorphism on C lambda star times Z in the case of Hodge modules. And Kashiwara and Kawai also announced a theorem, this type of theorem saying that this quasi-isomorphism extends to a quasi-isomorphism of C lambda times Z in the case of Hodge modules. So this is a generalization. So this is a generalization to the case of regular tree-study module. And by using this generalized Kashiwara-Kawai theorem and some additional argument, we can prove this theorem. And we can obtain some refinement of the functoriality of regular mixed tree-study modules with respect to direct image. And so for the first issue, so let me explain some outline of for the first issue. So let me remind you, we consider Taylor manifold with a holomorphic function such that the set of critical points is compact. And we can assume the set of critical points is connected and the critical value is 0. And so we have the mixed R module given by this Merot family of integrable connections, and which analyze mixed twistor divergence. And let pi 0 and p lambda denote the projection of c lambda times onto c lambda and x. Then this is actually, so we have the push forward, and the drum complex of LF is actually isomorphic to the twisted drum complex associated with the function f. So we'd like to prove this guy is free over the ring of formal power series. And so in the previous page, I explained some refinement of the functoriality of mixed twistor emoji with direct image. But the support of this is both of LF is not compact, so we can't apply it directly. And we replace this complex with several steps. So first, we consider the graph embedding of x into x times ct associated with the function f. And we consider, so let them denote the direct image of the structure shift, and let LT denotes the R module associated with the function t. Then there are also underlying mixed twistor modules. And then the push forward of LT is isomorphic to the tensor product of M and LT. And the push forward of the drum complex of LF is isomorphic to the drum complex of M tensor LT up to shift of 1. So the problem is replaced with the following problem. And we want to prove this guy is free over the ring of formal power series. And there you this the V filtration of this guy along t equals 0. And we have the morphism of shifts t plus lambda inverse from V minus 1 to lambda inverse to 0. And by considering the drum complex along the x directions, we obtain some double complex, and by taking the total complex, we obtain some complex C1 dot. Then it is standard. This C1 dot is isomorphic to this complex of shapes. So we would like to prove this guy is free over the ring of formal power series. And here we use some trick. I mean, we introduce some additional rescaling parameter. I mean, so we introduce one more parameter u, and we consider the complex of field on this bigger space. I mean, so pi 0, 1, 2 and pi 0, 3 is the projection onto 0, 1, 2 component or 0, 3 component. And then we consider the pullback of this shift by pi 0, 1, 2, and we replace del t plus lambda inverse by u del t plus lambda inverse. And so we obtain some complex C dot on this bigger space. And then the restriction of this complex to u equal 1 is C1 dot in the previous page. So we'd like to prove this guy is free over the ring of formal power series. And so we'd like to consider the intersection of formal neighborhood u equals 0, lambda equals 0, and u equals 1 here. But first we consider the restriction u equals 0. And we can prove this guy is free by using the functoriality of mixed twistor module. Actually, so we consider this one, the restriction of this complex to u equals 0. Actually, this guy is isomorphic to the drum complex of V0 over V minus 1. And and each graded pieces associated with refiltration under a mixed twistor D module. And if C is larger than -1, then the support is compact. Support is contained the quick this compact subset. Yeah. Yeah. So sorry. So -1. So if we call the negative integer, then the support it can be bigger. But if we consider just rational numbers and no integer numbers and 0, then support is contained in essentially contained in the set of critical point of view. Yeah. So we need some calculation, but this holds. Yeah. 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 Yes. So we use the so I assumed sorry. I assumed so the critical point is the set of critical is connected and it is, but this is not so essential because if we consider the formal completion, then the complex are separated. So we have only to consider each component. So this is not essential. And by shifting values, I mean, so twisted drum complex is considered df, so the value is not important. So this is not important. Yeah. Sorry. And so anyway, so Bullseye V, the support of Bullseye V is so if C is larger than -1, it is compact in those assumptions. So we can apply the theory of the defined factorial to mixed twistor module. This is a locally free O module. And then there is some standard argument to obtain this guy is locally free. So this is locally free. And then we study the formal completion along U equals 0. And I don't explain the detail, but there is some standard technique to obtain this guy is locally free from the locally freeness of the restriction to U equals 0. So in particular, we obtain the local freeness of the restriction to the formal neighborhood of 0, 0. And then we consider the different directions. I mean, by using the assumption the set of critical points is compact, we can show the restriction to lambda equals 0 coherent over OC. And so by using this, starting from this one, we can prove the restriction to lambda equals 0, formal neighborhood lambda equals 0 is coherent over this module, this algebra, shape of algebra. And so it implies, and so because this guy is, the restriction to the formal neighborhood of 0, 0 is free, locally free. So by using this coherence, we obtain that is locally free on a neighborhood of U equals 0. And by the construction, we have the C star equivalence of this guy. So we obtain we obtain the restriction to the formal neighborhood of lambda equals 0 is free. Then by taking the restriction to equal 1, we obtain the freeness of the desired freeness. So in this way, we can obtain the generalization of Baranikov concept theorem to the non-algebraic setting. So it is interesting to me to use one additional descaling parameter. So we'd like to discuss something over here. But first, we consider here, and on here we can apply the theory of mixed twistor D module. And then by using some argument, we obtain the results over here. So it is an interesting point to me. And this descaling parameter actually also appeared in the in the theory of irregular Hodge structures. So, which I'd like to discuss the next. So, irregular Hodge theory comes from the study of irregular Hodge filtration. And the idea of irregular Hodge filtration was originally introduced by Doreen. He studied this kind of twisted random complex in the one-dimensional case. And he introduced some filtrations and he proved the even degeneration of the spectral sequence. So as a result, he obtained some filtration on this twisted random cohomology group in the case the base space is 1. And it is now called the irregular Hodge filtrations. And Sava and you studied generalization of the Doreen idea in the different directions. And so they studied the higher dimensional case, and they, Eno and Sava and you proved the even degeneration of the associated spectral sequence. So they obtained the irregular Hodge filtration on the twisted random cohomology groups. They applied it to the study of concentric complexes. And Fresan and Sava and you applied the more general irregular Hodge filtrations in their study of some modular property of some functions, which was awarded in this conference. And after the works of Sava and you, and later by myself, irregular Hodge filtration were formulated as something attached with rescalable integral mixed twisted modules. And the rescalable objects are also useful for the study of the rigidity. So what would you like to discuss here? So let me explain some ingredients for algebraic integral mixed twisted module. So we consider only the algebraic case. So we consider the sheaf of algebraic functions and algebraic differential operators. And we consider the sheaf of logarithmic algebraic vector fields on C times x, which are logarithmic on 0 times x. And so we consider algebraic R tilde x as which is the sheaf of subalgebras generated in this sheaf generated by lambda times the algebraic logarithmic vector field on C times x. So for example, if x is an open subset of Cn, it is generated by lambda ZP and lambda square del lambda. And algebraic integral mixed twisted module is defined to be an algebraic Rx tilde module with some additional data and satisfying some conditions. And to consider rescalable objects, we introduce a morphism phi from C lambda times C times x to C lambda times x, given in this way. And so we can consider the pullback of algebraic R tilde x module by this morphism phi. And M is called rescalable if this pullback is also algebraic integral mixed twisted module. And so the irregular Hodge filtration is defined of the D module, underlying D module M is formulated in terms of the V filtration of this guy and the natural C structures. And we will also remark the standard functors for homoequivalent D modules are enhanced functors for rescalable integral mixed twisted modules. And we introduced, we considered the rescalable object to understand the irregular Hodge filtration. But it turned out it equivalent to exponential mixed Hodge module, which is a straightforward generalization of the exponential mixed Hodge structure introduced by Conway and Soibel. Algebraic mixed Hodge module is defined to be algebraic regular Hodge D module equipped with some filtration, good filtration, and basic structure with filtration, but it has some conditions. And the exponential mixed Hodge module is considered as Hodge module on xct times x, such that the direct image to x is 0. And then we have equivalence of exponential mixed Hodge module and the integral rescalable mixed twisted modules on x. And the equivalence is given in this way. So if we consider integral algebraic integral mix, if we consider exponential mixed Hodge module of Ct times x, then by considering this construction, we obtain the algebraic integral mixed study module of Ct times x. And we also have algebraic integral mixed study module of Ct times x associated with function t. So by taking tensor product and by taking the push forward, we obtain the scalable integral mixed t study module x. So this is equivalence of two objects. And we'd like to apply this equivalence to the study of the rigidity of Merlock flat bundles. And there's some conjectures about rigidity. I mean, so let me remind you, motivic D modules are defined to be the minimal class of conic D modules, which is closed and extension subquotient push forward products, and it contains OX for any algebraic multiplied x. And it is generalized to the extended motivic exponential D modules, which is defined by the same conditions, but OX and X are replaced by OX d plus dx and X, the pair of X and algebraic function F. And then there is a conjecture of constant. If conic D module satisfies X, Y, M equals 0, some rigidity condition, then M is contained in the class of extended motivic exponential D modules, which is a generalization of classical conjecture of Simpson. The conjecture of Simpson says if regular singular Merlock bundle is irreducible and rigid, then it is motivic. And this conjecture is very difficult and it's not beyond the scope of, but Simpson obtained some interesting results about this conjecture. Actually, Simpson discovered such a flat bundle always underlies a polar variation of Hodge structure. Sorry. Yeah, complex Hodge structure. Yes, exactly. And motivated by the conjecture of constraints, we obtain the following result. So let X denote a smooth complex projective variety with a simple normal crossing hypersurface. And we consider good Merlock flat bundle on X edge. And suppose V now is irreducible and X to 1 will equal 0. Then there exists the regular conic D module on Ct times X, such that M underlies the mixed Hodge module and X to 1 will equal 0, and V is obtained as the push forward of direct image of M tensor LT. LT is D module given this way. And so this is not solution of the conjecture quantity, but it reduces the problem for irregular singular Merlock flat bundles to the regular singular objects, at least in the case of Merlock flat bundles. And let me remark, Saba studied a similar issue in the case X equals P1 by using Arrington-Green cut algorithms. And so it is the idea is followed. So rigid Merlock flat bundle by using the generalization of Corrett and Donaldson and Hitch and Simpson theorem, we have the corresponding characteristic D module. And we also have, so from M, we can construct a mixed tensor D module whose underlying D module is end V. And by using some deformation theory, we can construct obstruction class here such that this class is 0 if and only if the action there exists an action lambda squared lambda compatible with Rx. And if this obstruction is 0, then the action lambda squared lambda is classified by this group. But so if this condition is satisfied, this space is 0, so obstruction is 0. And so under the irreducibility condition, this part is given by stress part. So if we fix the action on the determinant part, then the action is uniquely determined. So we can prove there is there exists a unique algebraic R-children module over M. And we can prove this guy is actually a scalable integralist module on X. And then by using the previous equivalence, it is described as the image of some mixed study module by B. And it implies the desired description of V, the desired description of V. So in this way, we can prove this kind of theory. So I stop here. Thank you very much. Sorry.
Thank you for this wonderful talk. So, do you have any questions or comments?
This here?
Yeah, so what's the
Yeah.
So you say that
Yeah, first we obtain some, we make some the general theory of deformation theory. And then we can construct obstruction theory, obstruction class for which, such that this class is zero if and only if there exists reaction lambda square del lambda compatible with Rx. And if this is zero, then reaction lambda square del lambda is classified by this space. And and so this is general theory without the assumption of this rigidity. And then if the rigidity is satisfied, then this part is zero. So obstruction class is zero. So we have some action of lambda square del lambda. And so under the assumption of the irreducibility and rigidity, this part is coming from the trace part of end V. So if we fix the action of lambda square del lambda on the determinant of M, then the action is uniquely determined. So yeah, so and so we obtain some unique algebraic R tilde module due by N. Yeah, and we can prove this guy is scalable integral mixed specialty module. So this is an analog of Simpson's theorem.
this is fixed by
irregular
CSI.
Yeah, and it is and by using equivalence, this equivalence, we can show this guy is described as the pushword. This guy comes from some mixed Hodge modules, and yeah, and then by taking the restriction to underlying D modules, we obtain this description.
Yeah. So yeah, actually, I get confused. So this is nothing to do with exponential motive. It's really just a connection with the singularity. But why you introduce exponential motive suddenly?
So yeah, but for this statement, yeah, we don't. For this in this statement, exponential Hodge module does not appear, but we use this equivalence.
Oh.
Yeah, so for this one, we use exponential the equivalence of exponential mixed Hodge module and the scalable integrable mixed Cincinnati module. So that is essentially used. Yeah, thank you for asking.
Any more questions? So, if not, then let's thank Professor Mochizuki.